When two black holes slam together, they don't make a sound. And yet, this is what we hear if we listen closely. Let's listen again. That chirp is what we heard from two black holes that slammed together about 1 billion light years from Earth. The tone rises as they spiral closer together and abruptly stops when they merge. But sound can't travel through the vacuum of space. So what exactly are we hearing? Each of these black holes weighs as much as several stars, hefty enough that as they pass through space, they make waves, gravitational waves specifically. These waves are undulations in the fabric of space-time that fan outwards at the speed of light, like ripples on a cosmic pond. Albert Einstein predicted this phenomenon in 1916 based on his theory of general relativity, but was skeptical that gravitational waves could ever be detected. Even the strong ones from colliding black holes produce ripples roughly 1,000th the size of a proton. It took almost a century for scientists to prove him wrong. Today, they have built and are expanding a global network of observatories that has so far detected gravitational waves from about 100 cosmic collisions. Recorded, analyzed, and converted to sound, each one's jostling of spacetime becomes its own distinctive, data-rich chirp. That long, low buildup is a sign of a slower, more sedate merger from relatively lightweight in-spiraling black holes. A more abrupt chirp, like this, is a sign of a faster merger of heavier black holes. In this case, a pair that combined to form one over 80 times the mass of our Sun. Now, after a long hiatus for upgrades in the COVID pandemic, the world's gravitational wave observatories are tuning back in to this celestial symphony. Gravitational wave observatories don't have mirrors or lenses like normal telescopes. Instead, they use lasers beamed down long tunnels laid out like L's with two arms laying flat against the ground. Bounced between mirrors at the ends of each arm, the lasers act like extremely sensitive violin strings. As gravitational waves pass through one laser's path, they repeatedly stretch and contract the space. Similarly, when a violinist uses vibrato, she shortens and lengthens her string. Convert all this laser vibrato to sound, and you can even hear black holes collide with a chirp. Cross-checking between these observatories confirms each event is more than random noise. If the same ripples appear in each one, they must come from somewhere in the sky. Timestamping a wave's exact arrival time in each arm of an observatory, and at each different observatory around the world, helps pinpoint the wave's direction and source location. And the chirps picked up by these detectors can sometimes reveal much more than the final moments of merging massive bodies. If astronomers get lucky enough to detect both gravitational waves and light from some celestial smash-up, as happened in 2017 with a neutron star merger called GW 170817, that rich dataset allows them to measure the expansion rate of the universe and perform better tests of Einstein's general relativity. GW 170817 even showed scientists how much gold, platinum, and other heavy metals these sorts of high-energy explosions hurl into the cosmos. Currently, there are 93 confirmed mergers, but during the next 18 months, astrophysicists hope to double their catalog of crashes, turning once rare chirps into a cosmic chorus, a growing soundscape of the universe's most epochal and otherwise silent collisions.